Welcome to the second part of lecture 27. We'll discuss in this part the effect of the bypass capacitor, and among other things, we can see here we have a capacitor C2 which bypasses the resistance RE. What if this capacitor is not there? What would be the effect on the circuit? So if this capacitor is there, for the AC analysis, RE is taken out, shorted. This will be our gain, this will be our input resistance. Now, if the capacitor is not there, it's open circuit. We don't have a bypass capacitor. Remember that RE dash, the base emitter resistance, is very small. It's few ohms, and it is in series with RE. And this is how all our results will be affected. The gain, instead of dividing it by a small number, RE dash, will be divided by a way bigger number, RE dash plus RE. This is few ohms. This is few hundred ohms. So this will result in a serious reduction in the gain. But on the other hand, removing the bypass capacitor will result in the input resistance. This is the same expression for the input resistance. You replace RE dash by RE dash plus RE. This is few ohms, this is few hundred ohms. Then you get a way higher input resistance, which is something desired in any amplifier, to have a very high input resistance. We usually select the bypass capacitors to have an impedance which is way smaller than the value of RE. Usually we select it to be 1/10 of the value of RE at the minimum frequency, and this is what this expression says. Remember that an impedance of a capacitor is 1 over j omega c. Then the maximum resistance, maximum impedance, is achieved at the minimum frequency. And this is why here we say we would like to have the maximum impedance here of this one, or what we'll call it without the J part here, is less than 0.1 RE. So it has to be very small in magnitude compared to RE, so that effectively shorts out RE. And if you write the expression that XC is 1 over omega C, and the maximum impedance is achieved at the minimum frequency, then at the minimum frequency of operation, this expression must be satisfied. So we pick the value of the bypass capacitor C2 that satisfies this expression. It must have an impedance whose magnitude, it will be at less than the modulus of its magnitude, less than 10% of the RE. So it effectively shorts out RE. Now we could see that having this bypass capacitor, it creates a benefit and it creates a problem. It reduces your gain because instead of dividing by RE dash, you divide by RE dash plus RE. But on the other hand, increases your input resistance, which is a desired feature in any amplifier. So we can try to make a compromise. Instead of fully bypassing RE dash, we can divide RE dash into RE1 and RE2. RE2 will be bypassed by the capacitor for the AC analysis, while RE1 will still be there. So this will result in an increase in the input resistance. We can see here. It will result in a reduction, but not that much in the gain. So we call this one partial swamping of RE dash, this approach here. So we try to reduce the gain a little bit, but on the other hand, we gain some input. One other reason for doing that is what's called the stability of the voltage gain. Most transistor parameters are functions of temperature. RE dash is very small. It's few ohms, and it does vary significantly with temperature. So if you have only in the denominator RE dash, as shown here, if there is no RE1, only RE dash, this may cause significant change in your gain if the transistor starts to heat or starts to cool down. And this is something not desired. So if this is few ohms, maybe add something which is way more stable with temperature, does not depend on temperature, increase the stability. It will reduce the gain, but it will also increase the stability. And as well, the input resistance will be more stable because instead of multiplying by a small number that varies significantly with temperature, you are multiplying by a bigger number that's more stable with temperature. So this is something that's very important to remember, that for all BJTs, most of the parameters are really temperature dependent. So we have three possible configurations: either completely non-bypassed case, and this one here will have a very high input resistance. The gain will drop because you replace RE dash by RE dash plus RE, and it's maximally stable because RE is way bigger than RE dash. The middle ground or the compromise simply to partially bypass RE by dividing it to RE1 to RE2. In that case, you get an average input resistance, moderate input resistance, moderate gain, and you get moderate stability, because if RE1 is not very big, then your effective resistance, which is RE dash plus RE1, will still change a little bit with temperature. The last one, which will give us the best gain, is simply to completely bypass RE, but this will make, as you can see here, our gain very dependent on temperature, because RE dash is dependent on temperature. This will give us minimum input resistance, because the input resistance is beta AC RE dash, and as we said, the stability, the gain will be maximum here in this case. So there is a compromise a designer will have to make when he is designing an amplifier. One other parameter we're interested in is the current gain. Current gain is simply the ratio between the current in the load, which we call here I out. And you notice how we define I out. We define it as flowing from the negative through the resistance. This is why it is not really a negative. It doesn't have a negative sign. If you define I out this way, then the gain will be negative. But the book of Floyd assumed that V out is measured plus or minus. Then V out is flowing this, I out is flowing this way, then the gain is positive. But we know there is a phase shift. This is something you have to keep in mind. So the ideal current gain is defined as the ratio between the collector current and the base current. And this one we can get very easily. It's beta AC. But the true, which is very high actually, that the true current gain or the overall current gain is simply I out over I source. The ratio between the current flowing in the output on the load resistance to the current drawn from the source. Okay, we know what's I out. It's VC over RL. If I divide VC from here to here, it's VC over RL. And we know what's I source. I source is simply the source voltage divided by RS plus R in total. We call this resistance looking onto Thevenin equivalent into looking to the right of this side. It's called R in total. If you're going to get the total power gain for a MOSFET, the total power gain was infinite because we don't draw really any input current. But here the overall power gain is the output power divided by the input power. The output power is VCI out, okay, the load resistance, and the input power is VSIS. You can divide that in VC over VS multiplied by out over IS. This will be the product of the overall voltage gain multiplied by the overall current gain. So this is an expression you can get for calculating the overall power gain of the amplifier. So this slide summarizes all the parameters we calculated. We are able to calculate the input resistance looking into the base. We can do that. We got an expression for that. We are able to calculate the total resistance after you include R1 and R2 and all the other things that you may have here. We are able to calculate the output resistance. You remove RL, you put an artificial source. We can calculate that after you remove your source, your signal source. We can calculate the ideal voltage gain. It is the ratio between VC and VB. We can calculate the overall voltage gain, the ratio between the output voltage to the source voltage. We can calculate the attenuation. We agreed that not all the signal from the source reaches the base. There is a voltage divider here, so you have to define this attenuation ratio. We define the ideal current gain. It is the ratio between IC over IB, which is simply beta AC. We defined also the overall current gain, which is I out over I source. We got already an expression for this one. So all these are parameters we can calculate for the common emitter amplifier.